All right, so let's go ahead and start the class. Be aware that assignment one is due tonight. How many people still need to finish their assignments? Like how many tasks are left? Anyone else wanna chime in? I'm considering where to give like extra credit for people who submit on time and then extend the deadline by maybe a 1 day. Uh, okay, so it seems like most of you are trying to fix like one or two questions that are left, right? I'll give you this choice. Basically, you can either submit by tonight and then we'll do the 10% extra credit. If you submit by tonight and you somehow manage to get, let's say, 90 points out of 100, I'll apply the 10%, which means that you're gonna get 99 out of 100. For those of you who want to submit it later, then you have until Wednesday night, but you won't get extra credit. So if you only have half of one of the question, you mean sending before midnight today, right? Essentially, if you submit before midnight today, I will apply 10% extra credit to your grade. Let's say you got 80 out of 100, I'll apply 10%, which means you are going to get 88 out of 100 instead of 80. If you choose to work on, let's say you only finish half of them, and you choose to, for those of you who submit already, you can keep working on it and submit like another submission on top of it. Just put in like put a comment on it on Canvas saying, hey, look at this version, or like never mind, go back to my old version. All right, so I'll do this by tonight. If you submit anytime before tonight, like before midnight tonight, I will. So if you want to resubmit, yes, please put in another 75 hash. Basically, I think Canvas support resubmission, so you can actually overwrite the old file. You have until Wednesday to do that. If you submit after midnight today, you won't get extra credit. If you overwrite your old submission, but that submission is after midnight today, you also don't get extra credit. For those who get the 10%, literally means that you submit before midnight today and there's no more submission. Like you don't overwrite your old submission. The last timestamp that I see on Canvas is before midnight, then the 10% apply. I hope this doesn't, basically this hopefully give everyone a little bit of room for time management and also a choice of, okay, do I want to kind of wrap everything up and submit by tonight, or I'll get more time, which mean also less time for the midterm, which is coming up, and then you will get no extra credit, right? Is that clear for everyone? The MD5 hash, you can just put it on comments, because basically when you submit onto Canvas, you can put in the comments. Just put the MD5 hash on the comments. All right, so let's look back at Wednesday. because we kind of not shifting over from, hey, let's write code in C to, okay, let's actually think about how did we understand the system and how does the hardware or the processor or the CPU understand what we're trying to tell them to do. So essentially, computer only knows 0 and 1, right? That hopefully that part is clear. You have high voltage and low voltage. That's either 0 or 1. That's also the reason why we want a binary number, right? Basically, what we have to do as a human to be able to control a computer is, okay, let's actually find a way to translate a human language into something that the computer can understand and take command of what we want them to do. Right? These commands are in a file called binary file. The reason why we call it binary files is it literally consists of a bunch of ones and zeros. It's just a bunch of ones and zeros where a computer would read from the first letter 101110011, and then it would look at this pattern and it would be able to tell, okay, if it's this particular pattern, this is what I have to do. So think of it as a way to interface between what we call as the assembly, which is, we'll cover that after the exam, the assembly code and the computer hardware, the computer circuits. So let's quickly think about what do I mean. I'm gonna start drawing things out, right? Let's think of this as the typical whiteboard. So this is what a computer sees. X-axis is time, and y-axis is basically voltage, right? I can see 0, 1, 0, 1, right? And then if you cut this by little chunks, like this, anything that has low voltage, it can be a 0. Anything that has high voltage is a 1. So this can mean something like 0, 0, 1, 1, 0, 1, 1, 0, right? What is the value that represents this particular bit pattern? That's 2, that's 4, that is 16, and that is 32, right? So it means 48 plus 4 plus 2, that's 54. So basically these particular signal, right, the signal that you see as a plot between voltage and time somehow can mean number 54. So you can see that these can be useful for computer to understand what the human is trying to tell them to do. These data is basically stored inside the memory, right? Which will then get read by the processor or the CPU as we know it. And then based on the instruction code, like in the ISA, which we're gonna cover a little bit more of that today at the ISA, it knows that, okay, this data means that you can do, say, for example, an add for basically do A plus B, for example. And that's how the computer can basically understand what we're trying to tell them to do. What is an A plus B in C? In C language, you can write it like this, right? When this gets translated all the way over to computer, it's going to be something that looks like this, where you have a signal over time with different bits, and then that becomes a proper means, like a value that means something. In this case, it means A plus B. And these main interface between the file, right? The file that's stored in Linux and your computer is done through the main memory, the DRAM. That is one of the most important interface in your computer. Why is that the case? You have the CPU on this side, right? And somehow you have all these files, which can be data files, for example, a graph, a text, an image, right? And then you can have also the binary file, which is basically your program, right? You also have things like network packet, which can come from your internet. For example, when you browse something on Chrome, the data doesn't magically appear. It actually gets transferred over from the server to your desktop, right? Through this network interface. Everything is interfaced through the memory. There are a lot of programs, which in this case we call a part of the kernel. How many of you heard of the word kernel before? Hello, are you up? Come on, wake up. All right. So yes, no, kernel. Have you might have heard something like OS kernel, Linux kernel, right? It basically it means the kernel usually means a core like core of something, right? In this case, it's a program that is a core that control the computer. So the kernel code, if you take the OS class, you see that okay, it actually has some part of the code that control how these files in the hard drive will be loaded to the main memory. Right? So basically they copy a bunch of these data program for the CPU to read from and write to, right? Read, write. Right? Basically all these bits, all these ones and zero will get transferred over to the main memory. The CPU would read from it. You've been dealing with pointers before. So where in this image is our pointer? Is it here or is it here? Is it the first arrow or is it the second arrow? The left arrow, the first one. Why is that the case? Pointer tells you where inside the memory we want to read the data from, right? Which is this. These are basically C pointer that we can use to read and write things to the main memory. And if we assume, right, if we assume that, hey, this is the main interface between any type of input and output of my computer, it interfaces with my keyboard, it interfaces with my monitor, it interfaces with my hard drive, it interfaces with my Ethernet cable, and basically these are called network interface. It interfaces all these things. It means that if I can read this location, I can do most things. And that's why knowing and being able to manipulate this pointer it can provide a lot of benefit. And how many language allows you to play with pointers? Not a lot, right? If you play with Python before, they don't even let you touch this pointer. Python would manage that accesses for you. In Java, it's the same thing. Exactly. The family of C will allow you to tell, okay, I want to go to that address because I know exactly what I am doing and I know why I need to access those address. And that's a big assumption, right? You need to know what you're doing, otherwise this becomes a downside. This becomes dangerous because you can actually walk into someone else's pointer and then the program can crash. And we talk about difference between data type, right? The character, integer, float. Then we talk about sign and unsigned. Right? So if you're curious about the difference between this, it's just how computer look at bit patterns, and it knows that, okay, I have to interpret each of these bit pattern in a different way, and that's all. Today we'll talk a little bit about more complex operation. By operations, I mean logical operations. The last time we talked about AND, OR, XOR, NOT, right? NAND and NOR. So, okay, I think this is one of my questions that I want to ask you. When you have negation, right? If I have the number 10 and somehow I want to convert this to negative 10, why can I do this? Why can I just do, instead of negative 10, I can do not n plus 1. Let me do a screen cap on the current attendance. If I'm told that I need to record the live sessions, showing that I'm actually teaching to submit to the OAA. But in any case, why is it okay to do not n plus 1 and then I'll get the negative value of n? Anyone want to take a guess? The hint is the two complements. So let's break the two complements down, right? Is everyone with me? Basically, let's assume we have one byte word. Let's assume this. Assume one byte of uh, of data. So what does this? Yes, exactly. Two complements. Basically, you flip out the bits and add one. The question then is, why do I flip it all back and add one again? You get a negative value of that. So we can actually use proper math to prove it, right? But let's do it slowly so that we all get the picture. So what is the value of 0, 0, 0, 1, 1, 1? How many ones is that? Okay, 1. This is 1 byte, right? What is the value of this? All right, everyone go grab a piece of paper and do some math. I hope that will wake you up. So what's the value of this? Yep, 31. So how do I represent 31s into two? This is a two complement format, right? So what is it basically? This is 0 multiplied by negative, oops, actually negative 1 multiplied by 2 to the 7, right? Plus 0 multiplied by 2 to the 6 plus 0 multiplied by 2 to the 5 plus 2 to the 4, 2 to the 3, 2 to the 2, 2 to the 1, 2 to the 0. What would happen if I just flip all the bit? Basically, you then get negative 2 to the 7, right? Plus 2 to the 6 plus 2 to the 5 plus the rest are all 0, right? Are you all with me? All right. So if I add these two numbers together, what do I get? Okay, again, please. Basically, if I do a negation on this, so if I negate, I do this, I will get 111, 0, 0, 0, 0, 0, 0, right? And 111, and then all zeros basically means that negative to the 7 plus 1 times to the 6 plus 1 times to the 5, the rest are all zeros, so it's plus 0. Yeah. So what if I add the two number up? Yeah, it's negative 1. It's not exactly negative 1, to be honest. If you add the two number out, it's something like this. So you are adding 0, 0, 0, 1, 1, 1, 1, 1, and then 1, 1, 1, 0, 0, 0, 0, 0, right? What will you get? What will you get? Sorry. What will you get from here? You get 1, 1, 1, 1, 1, 1, 1, 1. Right? If you add these two numbers up, you get all the ones. And that's negative 1, right? In the two's complement format, that's negative 1. How can I make it become 0? Add 1. Exactly, right? If I add these two number up and then I plus 1, what I'll get from here is basically 1s, right? And then 8, 0. There'll be 8 of them, right? And because our data is exactly 1 byte, right? The ones get cut out, right? So this basically means that if you negate n, right? You negate n plus 1 plus n, you get 0, right? The negation of n plus 1 plus n, if you just truncate into that 8 bits, you get 0. Yay, magic. Then what can you do? You know that, hey, then you move n here, right? Negation of n plus 1 equal negative n. Isn't that convenient? Just because we can just get rid of that one extra carry that somehow went away. It's get thrown away because we only have 8 bits. We get negation of n. I believe this is one of the answer to, I think, assignment 3. So at assignment 3 will ask you to do a bunch of tricks with and or negation, all these logic operations, so you can do complex things. So any questions about this? Any questions about why not n plus n and then plus 1 is 0 if you assume that you have the same number of bits of n? Because basically that ones get thrown out and then you can move n to the other side. It means that negative n equal not n plus 1. Or did I just lose everyone here? So can you type something if you understand what I'm saying? Because I don't mind kind of like reiterate this. Are you all with me? This is like what I'm scared of when I'm doing online classes. Okay, understood? All right, at least that's one person that say I understand. Could you re-explain? Okay, so I'll reiterate. So let me erase everything because it seems like a lot of people are still blank, right? So let me erase everything on this page and I'll do it again. Let's say I have one random number that have 8 bits. Right? So, oops. Can someone type me an 8-bit number? Any number? All right, 1110, 1100. Okay, that's our 8-bit number. So let's assume that's n, right? So let's assume that's n. What is negative n? What is the negation of n? My bad. What's the negation of n? Yep. 0, 0, 0, 1, 0, 0, 1, 1. I can't seem to write that one. Okay. So what? Yes. What if I add 1 to that? Well, actually, let's not add 1 yet. Actually, let's do this. I think it's easier to understand it this way. What if I add n and not n together? So what if I do n plus not n? What will I get? What? So I think because yes, because I write it in a way it's not actually aligned, but if you add the two numbers together, trust me, you get 1 1 1 1 1 1 1 1. Yeah, you get 1 1 1 1 1 1 1, right? And these are 8 bits number. These are 8 bits number. So what if I add 1 to both sides of this equation? So this is equation 1. So what if I add 1 to both sides, right? Basically, you get n plus not n plus 1 on the left side. What do you get here? You add 1 to this, you get 1 and 8 zeros, right? Are you all with me? And because our data is only 8 bits, what is this value? Because our data is 8 bit. In C, you just truncate. You cut it to the right. Basically, you cut it this way. This is our data. Yay. And you just forget about this one. So our data becomes 0. Right? So what you get here, n plus not n plus 1 equals 0. Yay, because we know that we don't have the hardware to support that one extra bit. It becomes 0. What if I add negative n to both sides of the equation? What if I add negative n to both sides of the equation? This is what I'll get, right? Not n plus 1 equal negative n. Yep. Anyone still have questions? Basically, these step is one of the key. If you add the two number and the number tends to overflow, this is called overflowing. Overflow into these bits that we cannot read them because we only have support to read eight bits. Each of these bits are literally read by wires. When you connect the wires together, that's the only way to communicate one bit. So the way it get cut is it start from the least significant bits and go from there, and it would just leave out the most significant bits. So the most significant bit is gone because we don't have room for that. So it gets thrown out. We are left with 0. All right. So without addition, basically, if you want to add the two numbers, this is what happened when we do say not n plus n, right? You basically only need to add the two number in binary. Carry bit will get discarded if overflow. Exactly the same case earlier, right? What if you want to add a signed number? Right? This is, let's say, unsigned int, right? So adding unsigned int is obvious. What if I need to add the signed number? This is what happened. Basically, exact same operation, and it still works. Why it works is because this is what happened. You add the two unsigned version, and then if you still assume that the resulting number is unsigned, is a signed number, you still get the same number as a plus b. What do I have to be careful about when I add the sign number? So let's say the maximum number of an integer is 32767. So if integer is 2 bytes, if integer is 2 bytes, sign integer will be capped at 32767. Basically, it will be between negative 32768 all the way to 32767. That's a valid 2 byte sign integer. So my question is, what if I add 32767 plus 1? Both are signed number. What will I get? Yep. It go around. Basically, it would go around from here all the way back to here. Right. So be careful when you deal with the sign number. It can flip into another, like a negative version of itself if you add it and it overflow. If you overflow, it doesn't get truncated or cut. It might flip the value into a negative number. If we add 2, you get negative 32767. Basically, the way it overflow is if you go above the limit, it starts from the maximum negative and go from there, step by step by step. And then to show why is this the case, right? This is a maximum positive, right? The basically it starts with 0 because 0 means that it's a positive number. The maximum positive number is 0 and then a bunch of ones, right? Zeros and then a bunch of ones. If I add 1 to that, what do I get? If I add 1 to that, I'll get ones and a bunch of zeros, right? Ones as a bunch of zeros is basically the maximum negative value I can have because the most significant bit represents -1 multiplied by 2 to that maximum value. And if you keep adding 1 to this, you're going to decrease this value one at a time because you keep adding 1 to this. So if you add, say, 3 to this, it is basically the same as you have the negative max int plus 2, right? Because when you add 1 to it, you get the negative max int, and then you still need to add 2 more. So you get 32766. And then there's this thing called true sum. Let me erase this part. My bad. So hard without the whiteboard here. If you have something called true sum, this is basically a summation, but we store the overflow bits. The overflow bits that go above the most significant bits, if that becomes a 1, some architecture, like an ARM architecture, can store that in a special register, in a special value that you can read from. You can check that, oh, okay, I add two numbers together and that overflow. So I can do something with it. What is subtraction? So what is subtraction? Assuming that we know how to add and we know how to negate. What if I want to do a minus b? What do I do here? Can I represent it with negation and addition? Yep. Well, yes. Not b, and you forget one thing. What is negative b? Yep. So that is not b plus 1, right? What does this tell us? If I need to build a hardware, what does this tell me? What can I save actually? What can I save? It is more or less, I don't need to build a subtractor. I only need an adder, and I need a way to negate. And then I can do subtract, right? I can save a lot of hardware, a lot of transistor, actually. Let's measure thing in transistor. I can reuse my adder to do a subtract, right? I can reuse my own adder to subtract. If you're in architecture class, then you might have an idea on like, okay, now that I have extra transistor, I can do other fancy things. It basically means that now you can reuse part of the hardware to do other operations, to save things so that you have the extra components to build something more fancy, to build a more fancy processor, to build a faster processor. So basically, if you want to do subtract, that is a plus, not b plus 1. Okay, this is the same thing. Basically, that this the above equation answer that. What if I want to do multiply by power of 2? I think I gave a hint earlier in the last lecture. So can someone refresh that that information for everyone else? So how can I do, say, a multiply by 8? What do I do? A multiply by 8. What can I do to 8? Actually, let's shift by 3 because 8 is 2 to the 3. Right? Basically, this is what happened. A multiplied by 8, right, is a multiplied by 2 to the 3. Right? Let's say this is a representation of a. Let's assume a equal. Right? Then a multiplied by 2 to the 3 is essentially, you have this same exact number, right? Same exact number multiplied by 2 to the 3, which means that I'm going to add 2 to the 3 into our the single bits here. So you're going to get 1, 1, 0, 1, 1, 0, 0, and add 2 more, and add 3 more zeros. And this is basically a multiplied by 2 to the 3. Yeah. So do you get why that is the case? I think let's make it a little bit more clear. So let me erase this again, right? What? Oops. What is a left shift by n? What is a left shift by n? Let's say a is 8 bits, so I'm going to cap it at 2 to the 7, right? Let's say this is a. A is a sub 7 multiplied by 2 to the 7 plus a sub 6 multiplied by 2 to the 6 plus a sub 5 multiplied by 2 to the 5 plus a sub 4 multiplied by 2 to the 4, and somehow I cannot write a sub 3 multiplied by 2 to the 3 plus a sub 2 to the 2 plus a1 multiplied by 2 plus a of 0. Right? Let's assume that's a, which is basically something like this. A7, A6, A5, A4, A3, A2, A1, A0. And that's a binary value of A. And you can replace A7 by either it's a 1 or it's a 0. And you get the value of A. Everyone is with me, right? Is everyone with me for this? Okay. So if I shift this by n, what will happen to all this 2 to the something? You get this, right? You get a, so a left shift by n is basically a of 7 multiplied by, yeah, you move the bits essentially. 7 plus n. Right? Plus a of 6 multiplied by 2 to the 6 plus n plus dot here because it applies to all the bits, right? Plus a sub 0, 2 to the 0 plus n. All right. With just simple math, this can be rewritten as a of 7 plus 2 to the 7. Oops. And then multiply by 2 to the n, right? Plus a6, 2 to the 6, 2 to the n, plus plus a0, 2 to the 0, 2 to the n, which means you can bring 2 to the n out of this whole thing, right? So you get 2 to the n multiplied by a7, 2 to the 7, plus a0, 2 to the 0. And this is the original a. So a left shifted by n is a multiplied by 2 to the n. How about division by the power of 2? Let's do the unsigned version first. This is logical right shift, right? Instead of multiply by 2 to the n, now you multiply by 2 to the negative n, the same thing. Any question about divide by power of 2? It is essentially the reverse of the earlier slides. All right. So we can kind of trick multiplication by doing this. Basically, we let's just do a proper multiplication first. If you have two n-bit numbers, I can produce a number that's up to 2 n bits, right? From n bits number, I can get 2 n bits. What you need to be careful is in a computer, they'll discard the extra n bits. You ended up with the same number of bits, right? So when you do a multiplied by b, be careful of overflow. That's my key message. Be careful of overflow. If it's going too far, your value could have become something that looks like 0 or some random number. So be careful when you do a multiplied by b. All right, making sure your data size is big enough to store everything. As I said earlier, from last Wednesday, I said that if I can do and, or, and not, I can build every single logic. If I can build any type of logic. I can build a fully functional Turing complete computer. It will be a Turing complete computer if I have an, or, and not. And because I can build an and, an or, and a not by a NAND gate or a NOR gate, basically if you have NAND and NOR, you can implement anything. These two bullet points will not be on your exam. I'll let you know that. I just want to give you the background and motivate you on like, okay, some of you might take in a digital design class, some of you might be thinking about the computer architecture class. These are some of the concepts that you might have learned from the other classes, and hopefully it makes a little bit more sense about how to build a computer and how to use C language and how to make things faster using and, or, and not to do many things. So this is basically what assignment 3 is about. You will then play around with bits, play around with logical operations, and your program will run faster. All right, so we're gonna shift gears here. We talk about how we represent data. We talk about logical operations. Now let's talk about the program itself. Right? I want to cover this material before we dive deeper into assembly. In the hope that you have a clearer picture of what is going on and why do I even need to learn assembly. In fact, I do a lot of hardware design personally, right? I still don't write assembly code. I would probably cry in a corner if someone told me to hack assembly code. And I think that applies to everyone in the world. But it's a good thing to know. It's a good thing to know because uh, at some point, you might have to deal with it. And yes, you have to sometimes cry in the corner, like, why do I have to do this? The reason is because sometimes you cannot fix a program and still make sure it runs quickly as fast as possible unless you hack the assembly code. But let's go back to what it means to have a computer. If we talk about we have the processing elements, you have the memory, and you have I/O, right? And these are the interface. Any questions about this? I think this is probably the third time you see these slides or a variation of these slides. Basically, the memory is where your program and your data is stored. It's probably the fifth time I said this. Well, hopefully, one thing you get out of this class is the executable program, whatever you run, is in the memory. Whatever data that the program needs to access is also in the memory. That's what I want to make sure you get out of this class. The memory is one of the most important things in computer world. That's where you store programs. That's where you store data. And also, if you need to make a program run really fast, most of the time it has to do with memory and how you manage it. And before, I think in the I think lecture 1 or lecture 2, I talk about this concept called instruction set architecture. Right? This is a concept that defines your assembly language. Basically, it's define a list of commands that the computer can understand and can do. And this is basically where assembly language come in. It would tell you if you want to add A and B, you need to write it this way. You might need to write it something like add 0, 1, 2, and these are something we call register. We'll go into detail in the next lecture. At this point, you just need to know that, hey, it has to be in this format. It's kind of like how you look at C as a language and you have to write ni j equal I plus 1. This is the same thing for assembly language. You need to write it in certain way. There'll be a document that tell you how you need to write it. The hardware part, we call this microarchitecture. Microarchitecture is what people like me who design a computer don't want programmer to see because it's way too complicated and you don't need to see it. But inside the hardware, these allow the add to happen, the subtract to happen, the multiply to happen, the if else to happen. Basically, we call this microarchitecture. And the processor, the CPU that you buy, is basically ISA plus the microarchitecture, the language that define how to drive the hardware, plus the hardware itself, right? It's the interface between software and circuits. So the third level bullet point there is kind of like partially a joke, but it's true. It allows you to not having to write things in binary, a bunch of zero and ones. But then you still need to talk in assembly, right? So it's still there's the gap here. And this gap we call it semantic gap. So let's get a little bit sidetracked. This is the gap between the software and the ISA. How many of you heard about the word syntax and the word semantic? Uh, uh, Not exactly when debugging all too often, but let me compare to an English like an English language, right? When I use a sentence, a syntax is grammar, right? Do I use it correctly? Do I say I don't know, I am talking? That's a proper way for English grammar, right? I should not say like I are talking or I is talking because the listener will be like, what the heck am I saying? I should use I am, right? Not I is or I are. The semantics means that regardless of the grammar, do I understand this paragraph? What does it mean? The semantic tells you kind of like, what does it mean? This text, what does it mean? The syntax govern how to properly write the text. Is that a clear distinction? Syntax is kind of like grammar that you need to write it in a certain way. Semantics is let's look at the text and do I understand what does the text mean? So semantic gap is something like when you write a program, it means something to you, right? As a programmer, you know that, okay, this is the if else statement that is inside the loop. Inside this if else statement, I'm going to increment things by one. And then from the computer point of view, they basically what they say is, I want one and zero. That's the only thing I know, right? That's the only thing I know how to say it. So a language that has a large semantic gap is something like you have an instruction that control the signal to command each circuit, right? And then the compiler would generate instruction that control the computer. As a programmer, you probably hate this kind of language. It's too low level. Something like assembly, right? You don't want to write things in assembly. So modern program has small semantic gap from the human language to the program language. Things like Python, Java. There's also the semantic gap for the ISA. The ISA in this case would look like a high-level language, which allow more application-specific hardware optimization. And there's a trade-off between one ISA to another ISA. Things like x86, which is what we will cover. That is a language that every single Intel processor and every single AMD processor understand. But then, if you have ARM processor that used in embedded system, or even your iPhone, they will not understand what any of the x86 assembly mean. Each ISA offer different level of semantic gaps. This can be done in hardware or software. This concept also applies to programming language. So if you take things like OPL, there'll be the same kind of discussion. how do we design a language? Right? Because each language has a different syntax, similar to how human language works. We have English, we have German, we have French. German, English, and French, at least they came from the same root, right? So there's some certain similarity. But if you compare English and Chinese, it's so different, right? The way it works is different. The way you structure the word is different. If you compare English to Japanese, it's even worse because in Japanese you put the order of the sentence is not subject, verb, object anymore. It starts with an object, right? So that's why each language offers different trade-offs, and similar happens to ISA. So what happens if ISA change a lot? Right? What happens if I have to change the ISA a lot? It means that somehow computers still need to understand this previous version of the ISA, right? Program that has no source code will stop working because the old ISA is not supported anymore. I don't know how to translate that language. For example, if I use x86, and let's assume that's the English language, right? So I have a processor that understands English and know what does the sentence mean. And then in the next 10 years, China took over everything and say, okay, everyone has to speak in Chinese. If you have a textbook in English and you give it to a new computer that only understands Chinese, they can't do anything. That's the same with ISA. Basically, if you give another computer that only understands certain ISA, and every single computer only understands one ISA. There's only one ISA that each computer understands. Your laptop, that's x86. Your mobile phone, that is a lot of time ARM. Right? And then for embedded device, there's multiple. So it means that if you have a source code, you have to optimize differently. You have to come up with a new compiler. You can also come up with another alternate solution, which is kind of translate. This is kind of like instead of having the Chinese person read English textbook, I have the translator that read the English textbook and translate that to a Chinese person. Right? So you can have the same thing in computer language. Transform one ISA into another. But in conclusion, having too many language is not a good idea. Having too many ISA is not a good idea. To be precise, having too many ISAs, it is a lot of overhead for the programmer, for the compiler, because they need to do a lot of things differently. Think of human language. If somehow English is not the most common language, and then if you're in like East Asia, you need to speak, say, Chinese. If you're in Southeast Asia, you need to speak, I don't know, like Thai. If you're in South Asia, you need to speak Hindi. If you're in the Middle East, you need to speak Arab. If you're in Europe, I don't know. You get the picture, right? Every time I move around to a different region, I need to somehow understand a different language, and there's no such thing as a central language that at least the English, right, that allow you to at least travel and communicate to some extent. And that's not convenient. So before we end this lecture, I want to kind of go over what goes into the ISA, right? What goes into the ISA and what you need to understand from this class once we start talking about assembly. The first thing is instruction. Instruction consists of opcode, addressing mode, data type. You go into detail in a bit. It talks about the register. Think of it as temporary variable. When you declare like int temp, that's behave almost like a register. You have access to the main memory. You have the concept of address space. We'll cover that in virtual memory. way later in this class. We will talk about addressability. We'll talk about alignment. That is something we'll cover when we talk about x86 assembly. And we'll talk about virtual memory management. That's toward the end of this class. And don't worry, I'm gonna throw right now I'm throwing a bunch of keywords. At some point, I'll make sure I have a way to put everything together, right? And I'll make sure that you at least have a high level idea of like, okay, for every single thing we learn about computer system, what would it look like if I had to put everything together? And that's the most important thing that you hopefully understand coming out of this class. What else? For completeness, this is more important in the OS class. That they would say, okay, how do we do function calls, interrupts, access control? How do I prevent Microsoft Word from reading data from Google Chrome? Priority, let's say in self-driving car, how can I make sure that the program that do object detection and see if someone is crossing the street has higher priority than another program that work on your radio, how to talk to the IO or the storage, keyboard monitor and everything, threat management, power and thermal management. That is actually important in modern day system where we cares about power consumption. As I said, no need to memorize this at all. That's a manual. Like if you go online, it's free. It's distributed by say Intel, ARM, whatever company that manufactured the processor. They'll tell you, okay, this is how it works. This is how you use it. So there's no need to memorize this. It's good to see some examples so you know where to start. And that's the next upcoming lecture. And let's zoom in a little bit on the instruction, right? This is most basic elements of the interface between you, software developers, and the hardware, the computer. It consists of two main components, something we call opcode and something we call operands. If I compare this to, say, instruction that someone tell you in English, right? If I say, go do in-class exercise, the verb is the opcode. Go work on in-class exercise. The go work on is the opcode. The operand is in-class exercise is the object, right? So basically, the opcode is a part of this binary value, ones and zeros, that tell you, is this an add? Is this a multiply? Is this negation? Is this an and? Or is this an or? Is this XOR? Is this if else? Is this a switch case, right? The operand tells you if, let's say, the opcode is an add, the operand would consist of C, A, and B, which might be the value C would equal to A plus B. The operand is the object. And here's the example, almost exact same example. Add R0, R1, R2, depending on how the ISA is defined, right? These vary from one ISA to another. You notice in the next lecture, it's actually a different format. But let's do, for example, here, R0, we basically add R0, R1, and R2 might means that I'm going to add R1 and R2 together and write the result to R0. Over here, R0 is the operands, R1 is the operands, R2 is the operands. What is my operators? The plus, right? And that's the difference between operands and operators. The opcode, it tells you what you have to do. Any questions about this? Because that's it for this class. All right. So if any of these are confusing, feel free to kind of ask a question going forward, or email me with a question. That's also fine as well. In the next lecture, because the exam is in 1 week, many of you asked about the format of the exam. So in the review session, we'll go over some sample exam questions, but please keep in mind, some of these exam questions are in-class exam. So the level of how open the exam is, it will be a little bit more open end. I'll ask you to kind of be creative, and hopefully basically there's no solution on the internet that you can just Google, but I'll make sure that it doesn't consume way too much of your time. My expectation is that you can kind of like finish everything in 1 hour, or at least I can finish everything in 1 hour. In your case, it might have to double, it might have to triple, but it would definitely be you should be able to finish it in the class setting. And for sure, you can finish it in 24 hours. So you have 24 hours to work on it. Come with questions, because the next lecture will be student driven. It will be almost the same as that lecture that we did earlier on the makeup class, that say, hey, let's do a review session, and if you have any question related to anything, sorry. Oh, sorry. But yeah, so come with questions. We'll go over, as I said, say sample exam questions. So hopefully you have a little bit better picture of what you might see on the exam. And for now, we have in class exercise 6, which is about bit operations. This is a preparation for your assignment 3. So I'm going to switch over to my desktop while I'm saving all this annotation so that I can post this PDF on the class website. So if you have any questions, feel free to remain in class, ask me questions, turn on microphone or whatever. I will be around to answer your questions until 4 o'clock. All right. In the meantime, go work on all the in-class exercises that you're left with. Actually, I do forget one thing. There's a question about in-class exercise 5 about the bookshelf question. Basically, it's kind of like a 3D array. So let me kind of visualize that particular question. So basically, the question is talking about, okay, you're in the library, you have multiple bookshelves, right? So this is in class 5. Right? You have multiple bookshelves, and you don't even know how many bookshelves are there. There can be many. Inside the shelf, you don't even know how many on the shelf, and inside each like each one of this, it can also contain multiple books, right? This is basically a 3D array. The simplest unit, the most zoom in unit are books, right? The books is your piece of data that you need to maintain. Inside the shelf, inside each level in the shelf, you can have multiple books, right? This is each one of these are books. And this is a shelf. Yes, exactly. So for exercise 6, implement this in C. I'm just going over in class exercise 5. So you can use basically a pointer to store each of these level inside the bookshelf that store a book, right? And then you can have another pointer that store the whole bookshelf, right? This pointer level 2. This is level 1. Right? And then this whole thing is stored in pointer level 3. Right? Basically, pointer level 3 will point to the pointer in level 2. Pointer in level 2 will point to the pointer level 1, which in that case is just one simple flat 1D array, and that's it. And then you might be curious about, okay, memory is a 1D space, so this is your memory, DRAM. Right? It's 1D. You start from address 0 to address whatever size your memory have. So each of these pointer will store inside this flat area. It's just going to be something like this. Let's say you look at pointer level 2, which point to pointer level 1, which then point to your data, right? So let's say this is level 1. This is level 2. Your pointer here would then point to the block of level 1, and the other one might be pointing to this block, which is also a different level 1, different level in the shelf. It would look something like this. So basically, it's going to be a pointer pointing everywhere in this flat DRAM address space. Yeah, so that's the whiteboard illustration of 3D array, basically. All right, so that's the end of the lecture. Oh, for exercise 5, just submit the code on the website because I do have an account as well. So basically what I do is I'll go there and see who submits. No need to actually submit on Canvas, but you can put in comments in case you have questions or whatever. That's for just for in class 5. For the rest, please submit on Canvas because otherwise I have no way to track. Let me save this. Quick. Sharing. Okay, I'm back on my desktop. Can you still hear me? All right, awesome. Yeah, so I'll be around for the questions. And the video from all the lecture are posted on YouTube. I haven't had actually time to go and trim the video. So the starting point and the end point is way like before and after the actual lecture. Sorry about that. I'll go and fix it whenever I have time. But both of them are online. It turns out WebEx is only buffering and sending the results only 2 days late. But it's there. Yes, next class is a review session. So feel free to come in with questions. I will answer the question in the first come first serve way. So if you want to come in, ask your question. Yeah. Yes. The exam is on June 1st, start at 2 p.m. If you have a valid reason to do an exam on June 3rd, let me know. I'll consider that case by case. For example, if you have 5 other exams on June 1st, please tell me. I don't want to be the 5th exam that make your life miserable, right? The actual content should be able to finish in 1 or 2 hours, depending on how fast you type and whether you run into random bugs. I mean, sometimes that takes time. I understand that. But yeah, it should be completed in a few hours. And it cover anything up to, basically cover anything up to like all this pointer manipulation, address allocation, anything from Linux and C. No, not today lesson. Actually, it's way before that. It's up to lecture 7. let me type it just for clarity. Lecture 1 to 7, not lecture 8, not lecture 9. 1 to 7. So think of it this way. Lecture 7, we talk about data structure. So there might be some question that asks you to implement something like that. There might be question from assignment 2, something similar to assignment 2. Definitely not going to be the question from assignment 2. But something that get asked in assignment 2 is something with the same difficulty, fair game. Yes.
We don't have class on June 3rd, is that because it's Queen's birthday, I think.
Yeah. Oh, okay. Good point. I totally forgot. Like, I feel like I forget every single holiday. And thank you so much for letting me know that I am about to schedule a class on a holiday. Okay. So that's a great question. I'll follow it up on. I think we'll do a. I'll do a recording on Friday, the usual time, 10 to noon. It's our midterm. Midterm is on June 1st. Midterm is on June 1st. All right. Exam is going to be more on C, to be honest. There'll be a bunch, like, there'll be some Linux question, but then it'll be I would say like maybe 60% Linux, 60 to 70% C, 40 to 30% Linux, something of that mix. I haven't have the final version of the exam yet. That's why it's still a range. And then let me go and modify. So lecture 10 will be on Friday, 10 to noon.
You mean this Friday or next Friday?
Next Friday. So let me type it in 3rd of June. I'll make an announcement on Canvas as well to make it clear. And to be honest, that class would be mostly about going over the exams. So that's why I want to do a makeup class, because I know that this can be kind of viewed later, and we'll go over some of the exam content and then kind of like, hey, let's bring out. Yeah. Nope, data representation is going toward the final. So anything from lecture 1 to 7 would be on exam. 8 to whatever that will come afterward.
อาจารย์ครับ exercise 6 นี่ทำเป็น array ใช่ไหมที่อาจารย์ bit zero storage
You can just use one single integer for that, actually. So basically, exercise 6, we want an input to be an array of character where each character represent 8 bits, and we can set or get any of those single bits. All right, so let me modify the calendar a little bit.
Yes, I do plan to curve the midterm if it come out weird. And I'm trying for my goal is I want to make sure that the result is not an inverse bell curve that that accidentally happened in the class you've taken with me last semester. So I will curve the midterm for sure. If there are questions that a lot of people get wrong, I will not curve. Basically, I'll make sure your grade will strictly either stay the same or go up. I won't curve it such that everyone have lower grade. That's not fair. All right.
อาจารย์ครับ unsigned character array ใน input ใน exercise 6 นี่คือจะเป็นis it like binary array
Yeah, treat it like a binary array. Basically, you can, if you want to be fancy, you can kind of use void star as well, but char star is a lot easier to work with. All right, so I updated the class calendar based on the additional holiday that we will run into, and yes.
อาจารย์ครับ get นี่คือ we get from character array right and the ix is the index so get basically just go to the array and find the index we want
The exact bits. The exact bits.
okay
So you can basically divide by 8 and
I thought that you can I like overthinking the question. I thought that we need to input the binary and get and translate the binary into integer, something like that. So,
basically it's a way to represent it's like a convenient way to access each byte because one character is 1 byte, so it kind of map well.
อาจารย์ครับ อันนี้ I asked just to make sure. So in C, right, when we need to run function, we need to put it in the main function, right?